I don't know what's happening to the attendance, but hopefully there'll be people 2 weeks into the class. I mean, 2 weeks later as well. So we were discussing dynamic optimization. And we were looking into the following sub-problem. And instead of looking at the optimal action, what we are instead looking for is a map or a policy which maps the state space to the action space. So some people use mu, some people use pi, some people use gamma. So depending on which literature you are looking at, different people use different notation for what a policy is, but all of them are basically the same. They map the current state into the current action. And what the principle of Bellman's principle of optimality said, it said that pi 0 to capital T star is optimal if and only if pi t to pi capital T star is optimal for every t. And this is optimal for every t for subproblem jt. So we look at a subproblem starting from time t. This tau is going from t all the way to capital T. So I'm looking at this subproblem starting from time t all the way up to the end of the horizon, and I'm going to try to optimize this subplan, get an optimal policy pi tau star for this particular subproblem. And then Bellman's principle of optimality says that the overall policy, overall pi 0 to T star is optimal if and only if the sub policy is optimal for the subproblem jt. This was established back in 1950s. I think it's 1952, but I may be wrong. So I'm going to add plus minus epsilon, so you kind of know that it's in that era. Okay. So this is Bellman's principle of optimality. Now, how do we derive an algorithm out of this principle? I mean, this requires a little bit of proof. It's not too hard, but it does require a proof. It's not obvious. One side is obvious. I think this side is obvious because if pi 0 to T star is optimal for the subproblem J0, then of course pi 0 to T star is optimal for the entire problem. That part is obvious, but the other way, which is if this is optimal, then the sub policy will be optimal for the subproblem. That part is complicated. But it does need a proof, and Bellman basically proved this particular result back in 1950s. Now the question is, how do we extract an algorithm out of it? Do you see an algorithm coming out of this result? If you were to solve this problem, what would you do? How do we come up with an algorithm? So the cool thing is, let me break it down. So this is saying pi t star is optimal for Jt, pi t minus 1 star, pi t star is optimal for Jt minus 1, and so on. So actually the algorithm is, let's try to solve the simpler problem first, then we'll go to the more complicated problem, then we'll go to the more complicated problem, and so on. Because the original problem is very complicated. Now I want to minimize over all pi 0 to capital T, I want to minimize J0. And that's a very complicated problem. And remember, you are minimizing over a function space. You are no longer minimizing over an action. You are no longer minimizing over Rn. You are actually minimizing over the entire set of function that maps xt to ut. So it's a very complicated optimization problem. I want to simplify this optimization problem. I want to come up with a sequence of sub-optimization problems to solve. And so this allows us to come up with a sequence of sub-optimization problems that we can solve in order to get pi t star and then get pi t minus 1 star, and so on and so forth. Any questions so far? Yes?
So we're optimizing the mapping?
We are optimizing the mapping.
Okay.
Yeah. Any other question? Yes?
So policy is defined for multiple time steps, and the function f is defined at each single time step. Is that correct?
So pi t is defined for time step t, and this actually is a function of xt and it outputs ut. Okay, so it tells you for every state what is it that you are supposed to do. If you are launching a rocket, it tells you what you should do at the ground level, what you should do at 5 meters above the ground, 10 meters above the ground, 20 meters above the ground, 5,000 meters above the ground, and 50,000 meters above the ground. So it basically tells you what you need to do at every point of time and at every state that you will be at.
So the function f also takes the current state and the current action to get the next step.
That's right.
But that's only taking just the current state.
This is the state transition function. So there are a lot of functions here. There is a cost function, there is a state transition function, and then there is a policy. Okay? So policy is telling you how you should act based on the state. State transition function is telling you, given the state and action, what the next state is going to be. And then the cost function is telling you, given the state and action, what is the cost you are going to incur. Okay? So think about it from a rocket perspective. If you are at 100 meters and this is the action you pick, you will be at 110 meters at the next time step. The policy will tell you what you should do when you are at 100 meters, right? What action you should be picking when you are at 100 meters height. And then the cost function is telling you how much rocket fuel you are spending going from 100 meters to 110 meters. Okay? So that's what the overall idea is. And I want to minimize the total amount of fuel subject to the dynamical constraint of the system, and I want to find a policy that maps the state to action. This was not the case in the minimum principle. We just wanted to find the optimal action. We didn't care about the policy. But the drawback was, if I happen to deviate because the wind was blowing, then I have to recompute everything all over again. Now we don't have to recompute. I mean, it will turn out that we won't have to recompute because we have the policy which automatically tells you what you need to do at every state. Yeah?
Is there some kind of tie-in with reinforcement learning?
It is, yeah. I mean, we'll not get to reinforcement learning in this class, There's another class, ECE 7252 or whatever, that talks about reinforcement learning. But yeah, this is the precursor to reinforcement learning discussion. Yeah.
It always stays on the most optimal trajectory because all the successive policies are also optimal.
That's right. That's exactly what the situation is. So if the wind blew and instead of xt star you are now at xt star plus epsilon, this policy will tell you what you need to do at that particular point, because it's a function of state to action. So it will tell you at every state what you should be doing. Okay, so if you think about it from, let's say, the chess perspective, right? So when you're playing chess, it's one thing to say, oh, move your horse, move your elephant, whatever, all of that, pawns here and there. It's another thing to say, if this is what the chessboard looks like, if this is where the adversaries' pawns are, then this is the move that will be the best move for you, right? So that's a difference between open loop policy, which is UT star, versus closed loop policy, which is a function of the state. Okay, so you are observing what's happening, and then on that basis you are taking an action.
What do you mean by open or closed loop?
So UT star, when we talked about in the Pontryagin principle, you get UT star directly. It's not a function of anything. Okay, so it's an open loop policy. It's like me telling you, you want to go to a coffee shop, just walk 100 steps and you will reach the coffee shop. And then you basically, I don't know, like if your step is, my step is 80 centimeters per step and your step is 75 centimeters per step, then of course we don't agree on the definition of a step. And so you will not reach the coffee shop, but I will reach the coffee shop in 100 steps. But so that's open loop. You're not taking feedback into account. You're not looking at the distance to the coffee shop and then making sure that you take this additional step to get to the coffee shop, right? Closed loop means that you are taking into account what the current state is. Okay. Any other question? So let's try to look at what this problem statement is. So I want to minimize Ct plus 1 xt plus 1 plus Ct xt ut. I want to minimize over all pi capital T that maps xt to ut. And I have this constraint, the dynamical constraint, right? This is the problem I need to solve. The argmin is pi t star. And of course ut is equal to pi t xt. How should we solve it?
Looks like argmin, so we should take the gradient.
But remember that this is a functional optimization problem. You are minimizing a function, not a vector. Here is how we will do it. So here is how we will solve this problem. I am going to define pi t star of xt to be the argmin over ut of Ct plus 1. Now remember, I have this constraint, dynamical constraint, so I am going to eliminate xt plus 1 and I am going to substitute this particular function, and so I get ft of xt ut and this ut is in, sorry, u capital T. This is in u capital T, and this hopefully u capital T would be Rm. And now what I have done is the policy evaluated at xt is actually a solution to an unconstrained optimization problem in that case. So of course ut could be a convex constraint, it could be unconstrained. So for now let's just assume that these are unconstrained, but you know how to solve a constrained optimization problem also, so I guess it doesn't matter if ut is unconstrained or constrained, but you can solve this optimization for every value of xt. So conceptually, in order to find the pi t star, what you have to do is you have to look at every state xt, you have to solve this optimization problem at every state xt, store that as a function. How do you store a function in a computer? So let's think about it. This is my x capital T, this is my u capital T. So I'm going to compute the solution, I'm going to discretize the space, I'm going to look at, okay, this is the value of ut star here, this is ut star here, this is ut star. So at every point in the state space, I have computed what my ut star is going to look like by solving this particular problem. Now how do I store this function? Maybe this function looks something like this. How do I store that function? No idea? Yeah.
Just like a two-column vector, one is xt and one's ut.
Wonderful. Yeah. So one way to do it is by storing it as a by storing it in this particular format. Well, in a JSON format. So what would a JSON format look like? xt1 ut1 xt2 ut2 and so on. So this would be a vector and this would be another vector, this would be a vector, this would be another vector. So that's one way to store it. The other way to store it would be xt1 xtn and ut1 utn. This could be another way to store it in the form of a matrix. Alternatively, you can give this as a training data to a neural network solver or to a polynomial generator out of the data, and then you can store that polynomial coefficients or the neural network coefficients as in your memory, and that's your function. That's how you would store a function in the memory, in a computer memory. So we'll get to it in a bit, but conceptually this is what you need to do, and then how to store it in the memory is something we'll talk about probably on Friday's class, where we talk about approximate dynamic programming. Yeah.
I can see how you got rid of the first constant because you substituted it, but how did you get rid of the second constant?
So the second constant, this one, right? Yeah. So the way I got rid of it is I'm now directly optimizing ut and I'm storing it as pi t star. I'm no longer optimizing. So I had a functional optimization problem. Now I'm converting it into a finite dimensional optimization problem at the expense of solving that optimization 1 million times. So if I wanted to solve this problem, I'll get pi t star directly, but I can't solve an infinite dimensional optimization problem.
So when you say we will try that be pi t?
That will be pi t star. In fact, it will be an approximation to pi t star. So the true pi t star we will never know except in some special circumstances. So we'll talk about those circumstances in the next class. Any other question? Okay. So this is how I will compute pi t star. Now what I am going to do is also store another function called the value function Vt of xt, and this is minimum over all ut of this particular function. So that's this. So the argument is stored in pi t star, and the minimum value is stored in what is known as a value function. So this is optimal policy. And this is the value function. And by the way, this function here is called cost to go function. Cost to go function at time capital T. This is value function at time capital T. This is optimal policy at time capital T. So let's look at the train of thought. We started with an optimization problem which was very complicated. Bellman made it even more complicated by saying that instead of optimizing action, let's optimize plan. Okay? So he made it complicated, but then he simplified it and said that, look, I know that this is what we are interested in, but it turns out that if this is optimal, then the sub policy is optimal for the sub problem. Then that gave us an idea that, okay, let's try to solve the sub problem at time capital T and at least get pi t star. We can't find the entire thing, but let's at least find out what pi t star is. Then we moved on to an optimization, sub-optimization problem at time t, and we realized, oh my God, this is a function optimization problem. I don't know how to solve a function optimization problem. Life is really bad. Then again, it turned out that, okay, instead of trying to solve this complicated function optimization problem, let's try to solve this problem one step at a time. Let's pick a value of xt, solve this optimization problem. I'm going to store the argument in this particular function pi t star, and I'm going to solve the minimum in this function called Vt, which is a value function. And what am I minimizing? I'm minimizing the cost to go function at time capital T.
So the optimal policy is just a grid search, as you said?
In this case, I am talking about grid search, yeah. There are many ways to find out the optimal policy. So right now, the simplest one is the grid search. Just figure out, just discretize the state space xt and then solve this cost to go function as a function of ut. Just solve it using sequential quadratic programming, optimization over convex set, unconstrained optimization, whatever works for this problem. And then find ut star and then store it in this particular matrix. I mean, I'm calling it a matrix, but it's not a matrix. It's some function, some map like this. Okay. So at least we were able to get this off our to-do list. Now this is on our to-do list. How do we solve this problem? What do we do the cool thing is, I seem to have already computed this, right? This part is already computed. So it turns out I only have to compute this. I only have to compute this. So what I'll do is, I want to minimize over pi t minus 1, Ct minus 1 So it turns out I need to solve this problem. Because pi t star is already known, I have already computed it right here. So I'm just going to substitute the pi t star for the time for ut, and I'm going to substitute pi t star here in the place of ut. So what do I get now? I get something where, okay, so I have x t minus 1, no, x t equals to f t x t minus 1 u t minus 1. That's the constraint, and then u t minus 1 pi t minus 1 x t minus 1. How can we simplify that? It still looks too complicated to me. I love simplicity. I think there is some similarity between the problem here and the problem here. So I have this function of state and action, I have the function of state and action, then I have this complicated function, a sum of two functions, but here I only have a simple function of xt plus 1. But wait a minute, if I observe these two functions, it's a function of xt, it's a function of xt, it's a function of xt, it's a function of xt. So this whole thing actually is a function of xt, just like in this case I had a function of xt plus 1. Right? I had a function of the next state. So I'm looking at the subproblem at t minus 1, and I found this block of quantity that actually is just a function of xt, which is the next state, just like it was the case here. I had a function of the next state. Rest of it looks basically the same. What is this thing in the block equal to? Yeah. It's equal to Vt of xt, because remember this is the minimum of the cost to go. And so if you replace, remember pi t star xt is actually the minimum value, the argmin. So if I replace pi t star xt here, pi t star xt here, then I actually get the value function here. So actually this is equivalent to saying I want to minimize over pi t minus 1 Ct minus 1 Okay, I was able to simplify it. Now I feel better about my existence. I was able to get exactly a problem exactly in this particular format. I have a function, the cost function of the current state and current action, and a function of the future state, and I have the state transition function, and I have the action as a function of policy. How do I solve it? I solve it exactly in this particular way. Okay. I'm going to write it as minimum over ut minus 1 of Ct minus 1 plus Vt, V capital T composition Ft minus 1, and this whole thing is a function of xt minus 1 and ut minus 1. At every xt minus 1, I am going to solve this minimization problem over ut minus 1, and I am going to store it as an optimal policy pi t minus 1 and as a value function Vt minus 1. And I get by solving this minimization problem, I get pi t minus 1 star and then Vt minus 1. I get the value the optimal policy at t minus 1 and I get the value function at t minus 1, and this is my cost to go function. This is my cost to go function at t minus 1. So cost to go is the current cost plus future optimal cost. So now, has everyone written it down? Okay. So now I have been able to compute pi t star, I have been able to compute pi t minus 1 star. So the second task is also off the to-do list, and then I can keep going down the path and compute pi t minus 2 star, pi t minus 3 star, pi t minus 4 star all the way up to pi 0 star. And then I'll get the entire optimal policy. Okay. So the reason why computing the optimal policy in this way leads to the optimal policy of the entire problem is because of the Bellman's principle for optimality, because at every point of time we are ensuring that pi t to capital T star is optimal for the subproblem Jt. Wonderful. So that this algorithm is known as a dynamic programming algorithm. Don't ask me why it's called dynamic programming. Oh, actually, maybe, so this is my hypothesis. This is why it's called dynamic programming. So in 1940s, optimization was known as programming. So you weren't an optimizer, you were a programmer in 1940s. Okay. So this is programming for a dynamic problem. So that's why it's called dynamic programming. Okay, that's my hypothesis. That's why it's called dynamic programming. Okay. Any questions so far?
How does this not, like, it seems like this would become more and more computationally complicated as you approach the horizon. How does it?
Absolutely. So that's the pro and cons. So let's talk about pros and cons of this particular algorithm. What's the pro of this particular algorithm? We get a closed loop solution. A closed loop policy. Closed loop optimal policy. Anything else that you find cool about this algorithm? It satisfies sufficient condition for optimality. Pontryagin minimum principle was satisfying only the necessary condition for optimality. So this one satisfies sufficient condition because of Bellman's principle of optimality. But remember, we are really talking about apples and oranges. So this is sufficient condition for optimality of closed loop policies, okay? Whereas minimum principle was satisfying necessary condition for optimality of open loop policies. So there's a slight difference in the two approaches. We are talking about plans here, we are not talking about open loop policy in this particular situation. Any other pro that you can think of?
So is that not referring to positive semi-definiteness of the cost?
No, you don't have to check for positive semi-definiteness of the cost. As long as you can compute the argmin, you are essentially minimizing the entire optimization problem. So remember that this could be a non-convex problem, and so instead of arriving at argmin, you might come to a local minimum, in which case it's an approximately, so it's an approximate optimal, not the true optimal. So for true optimal, you need to be at argmin at all points of time.
But you can still approximate. You can still approximate the right solution even if you have a lot of non-convexity in your program.
What do you mean by you can approximate? Like by discretization of the action space as well?
Maybe I'm not sure what I'm asking. I'm trying to think of if the problem is highly non-convex, how would you ensure that you converge to something you would want? Like how do you not overshoot something entirely?
Right, so good question. So if this particular stuff is non-convex, if this is non-convex, then even if you are running a gradient descent algorithm, you may not converge to the optimal solution. In which case, this whatever argmin you have computed is actually a local minima, and therefore you are no longer optimal in the true sense of optimality. You are essentially suboptimal, but sometimes suboptimal is good enough.
Does it not add up over time though? If it's suboptimal here, then the next step might be suboptimal.
It does, but if it works in practice, it works in practice. Then you don't try to question the suboptimality. Okay? So if you think about all the stuff that Google is doing, and so I'm going a little bit on the tangent, but basically this algorithm is used for recommendation systems, for instance, right? Now, if it gives you better recommendation system than what I could concoct in like one afternoon, then of course, and you're making millions of dollars, then who's going to question? Like Netflix doesn't care if you're at a local minimum or a global minimum, right? As long as it can recommend appropriate movies to you and you spend 5 hours watching those movies and TV shows. Right? So that's what happens. But of course, people are always looking for better and better approaches for solving problems in specific domains so that they're always at the truly global minima. Yes?
So the closed loop over here means that because we are also considering the successive policies,
Mm-hmm.
it does not exactly mean like once the rocket is in the air, now a bird suddenly comes in, so everything's again optimized. Like it's not like external environment that's making.
So whatever external environment does, it moves it from the optimal path of xt star to something which is xt star plus epsilon. Right? So this was your x1 star, this is x0 star, x2 star, x3 star, and x capital T star. This was your optimal trajectory, but because of the wind and because of the bird, you basically are going like this, right? But the good thing is, because pi t star is a function of xt, you know exactly what you need to do at each of these points, right?
But all of this policy is completed before the rocket is allowed to go.
Yes, but the good thing is you only need to compute the policy once, but it is optimal for the entire duration. Remember this statement. For every sub-problem, pi t to t star is optimal. And this is an if and only if condition. So that comes to our rescue, that you don't have to recompute the optimization every time you are off the optimal path. So that's actually the third pro. No need to recompute.
By recomputing, you mean recomputing pi 0?
Yeah, you don't have to recompute pi 0 to t star. Actually, the other pro is it's strongly time consistent. Which is basically the same as 3. These two are basically the same thing. So a strongly time consistent policy means you don't need to recompute the policy every time you are off the optimal trajectory. So it's the same thing. Third and fourth is the same thing. Fourth is just a technical way of saying it. Third is colloquial way of saying the same thing. Okay. What are the cons? So we studied some pros of this particular policy, this algorithm. First is computationally demanding. So at every point of time and for every value of xt, you have to solve this minimization problem. How much time does it take for gradient descent to converge? Few milliseconds. So for every state, you have to spend a few milliseconds computing this optimal solution. How many xt's will be there? Let's say it's a 5-dimensional space. You have 100 points along each of the dimension. Then you have 10 square raised to 5. So 10 raised to 10 different states at which you need to compute this argmin. So you have to do, if each of this argmin takes 1 millisecond, you have 10 raised to 10 xt's, then you have to spend 10 raised to 10 milliseconds to solve, to get 1 pi t star, which is 10 raised to 7 seconds, which is 100 days. So it takes 100 days for computing 1 pi t star and Vt. And then you multiply it by capital T time steps. How many time steps we had in the rocket problem? 1.8 million. So 1.8 million into 100 days. So 180 million days is needed to solve this problem. The rocket problem, if you want to solve it using dynamic programming. So saying that it is computationally demanding is actually an understatement. But that's what it is. It does take a lot of effort to solve this problem. Computationally demanding. Anything else? Any other cons that you can think of?
I think he said it like there's a lot of approximation.
Lot of approximation, yeah. In fact, storing it in memory is also a very big challenge. How are you going to store 10 raised to 10 variables multiplied by 1.8 million such functions? So storage is also a big problem. There's another problem that comes in. That's because if you have stored the pi t star and Vt star, then whenever you are doing this optimization, the cost to go optimization, you have to do some interpolation of Vt. So that interpolation is also challenging.
Can you repeat why you need to interpolate?
Yeah, so I'll repeat it. Let me rewrite that optimization here. This is argmin. right? This is the problem I want to solve. How have I stored Vt in my memory, Vt plus 1 in my memory? So I have, let's say, xt plus 1 equals to 0, and the corresponding Vt plus 1 of xt plus 1 equals to 0 is equal to, let me put some number here, 0.5, and I have xt plus 1 equals to 1, and Vt plus 1, xt plus 1 equals to 1 is equal to 1.5, right? This is how I have stored my value function. This is storage of my pi t star and Vt star. Oh, I've used Vt star, but Vt doesn't come with a star. Some people put a star, some people don't, I don't. So I'll just use Vt plus 1 as the optimal value. Now, I picked a specific xt and I picked a specific ut, and I'm trying to evaluate this function, or I'm trying to evaluate the gradient of this particular function. Now, turns out that ft of xt ut is equal to 0.5. But I don't have xt plus 1 equals to 0.5 stored here, right? I don't have the value function at 0.5. So now I have to interpolate between xt plus 1 equals to 0 and xt plus 1 equals to 1. I have to interpolate in order to get the value function at xt plus 1 equals to 0.5, right? So you need to do the interpolation at every point of time, and that makes the computation even more challenging. Any other question?
So you could use a neural network, can we just avoid this?
Yeah, then you avoid this. So the way to train neural network then is to take this input-output equation, like this is the x and this is the y, and then you train a neural network of using this xi, yi, and then you don't have to worry about the interpolation part. So neural network does the entire interpolation. And in fact, computing gradient also doesn't become a problem, because now you know how to differentiate neural network. We covered it in the previous class. So that also makes it easy to compute the derivative. Any other question? No? Okay. I want to add one more comment here, which is, suppose you have this constraint at every point of time. So I have the same problem right here, but now I have a constraint that gt xt ut less than equal to 0, ht xt ut is equal to 0. I have this is known as a state action constraint. So if you are at 70 miles an hour, then this much emission is allowed. If you are at 30 miles an hour, then this much emission is allowed, so on and so forth. If your battery pack is completely full, this is how you discharge the battery. If your battery pack is half full, this is how you discharge the battery. So the state action constraint basically allows you to capture a lot of these constraints on the actions, what is allowable and what is not allowable, as a function of the state that you are in. That's captured by the state action constraint. So we have two types of constraint. One is the equality constraint. So this is kind of an equality constraint, state action equality constraint. But you can have other kind of equality constraints as well. And then you have the inequality constraint, and so you have a bunch of state action constraint. In the context of autonomous driving, if you're driving at 70 miles an hour, the safety distance with respect to the vehicle in front has to be 10 meters. But if you're driving at 2 miles an hour, then it can be 1 meter, right? So those are all captured here in this, like a whole bunch of constraint. And then if you're solving the problem, all you have to do is just add these constraints here.
Shouldn't that make the problem easier?
No, it doesn't. It makes it more complicated. So you were solving unconstrained optimization problem earlier, now you have like two constraints. So now you have to do sequential quadratic programming or method of multipliers or one of those four methods that we talked about. So you apply one of those four methods to solve this problem. Right? It's not easy, but it's not conceptually everything works out beautifully. Practically in the implementation, a lot of things goes wrong. Okay, so writing an algorithm for solving unconstrained optimization is very easy. Debugging it is very easy. Communicating it to someone else, to your manager, is very easy. Now you add a bunch of constraints. Now you are implementing some sequential quadratic programming. Some plus became minus, some minus became plus. Now you keep debugging it for hours and hours and hours, and you don't know where the bug is, and so on and so forth. So it just takes a lot of time to, again, conceptually everything is easy, just implementation and debugging and communicating it to other people, and so imagine if you have to do this on an automotive microcontroller. It's just a nightmare to do it. Okay, so that's predominantly the reason why people have not used optimization very heavily in vehicles, but now they have started working on optimizing each and every component of the vehicle. So now they are optimizing the air conditioning system, they are optimizing the fuel consumption system, they are optimizing the cylinder firing system, they are optimizing each aspect of the vehicle to minimize the fuel consumption, and that's because solving these problems are very difficult.
And that's because we're putting more powerful computers on them? Or?
Yeah, so part of it is because you can afford more powerful computers. You can also charge people more, like this is a $35,000 car, but it has like all bells and whistles and lane keeping assist and I don't know, some 500 warnings that comes out of that infotainment system. So all of that bells and whistles, they charge you for it, but then they put powerful processors in it. So they are paying the cost as well of both the development, debugging, and making sure that it is production ready. And remember, the vehicle's problem is also that all of this stuff should work 10 years after the vehicle was sold and after 500 parts were changed in the vehicle. So it's not that easy and straightforward, but they are able to do it now. So that's all I wanted to talk about today. Then in the next class, I'm going to solve a linear quadratic optimal control problem using this principle of dynamic programming. So that's going to consume our next class. And then we'll talk about, then next Monday there is no class because it's holiday. And then Wednesday we have midterm, and then next class will be Friday next week. Okay. Awesome. Thank you so much, and we'll meet again on Friday. Oh.